Here we look at bond enthalpies. Within the chapter of bond enthalpies, there is a couple of definitions that you should be aware of. What is bond enthalpy? Well, it's the enthalpy change for breaking a mole of a particular covalent bond in the gas phase to form gaseous atoms. And another definition, probably more important one, is what mean bond enthalpy is. And mean bond enthalpy is the average enthalpy change for breaking one mole of a particular covalent bond in a range of different compounds in the gas phase. And we can use these mean bond enthalpies to work out a theoretical enthalpy change for a particular reaction. And we can do that by using the following equation, and it's an equation you need to be able to remember and apply. That the enthalpy change of a reaction is the sum of the mean bond enthalpy of the bonds broken minus the sum of the mean bond enthalpies of the bonds formed. So this is an equation that you need to be able to learn. Okay, and that's one that we're going to use now to answer a couple of questions involving mean bond enthalpies. So I've got a question now where I've got to calculate the enthalpy change for this particular reaction. It's a reaction of hydrazine with hydrogen peroxide to produce nitrogen and water vapour. And in a reaction like this, we need to know the type of bonds involved in the reactants and products. And hydrazine involves a nitrogen-nitrogen bond and 4 NH bonds. Hydrogen peroxide is as follows. Nitrogen is a triple bond and water is obviously as follows. Now, in an unfamiliar reaction, you'll probably get this data here given, but for reactions like enthalpies of combustion, you'd have to know the type of bonds involved in the reactants and products. Now, it says we've got to calculate the enthalpy change then from this reaction given the mean bond enthalpies in the table here. What you should be doing in a question like this is firstly making a column for the amount of energy needed to break the bonds. So bonds broken. And we can see that we've got 1, 2, 3, 4 NH bonds. So I've got 4 NH, and that is equal to 4 times, and let's just check, it's 4 times 388. When you worked it out, you end up with 1552. You can see that we've got an NN bond there, so that's 1 NN. And that is equal to 1 times 163, which is obviously 163. And we've also got 2 OO bonds, because we've got 2, remember, H2O2, so I've got 2 of these molecules, so I'm going to break 2 OO bonds, which is 2 times 146, which is 292. And I've also got here 4 OH bonds, 2 OH bonds per molecule. So I've got 4 OHs. That's equal to 4 times 463. And that then is equal to 1852. So what you do then is you add up all these numbers, and when you do that, you get 3859. That's likely to get you 1 mark in an exam. So you need to be able to work out the energy required to break the bonds. Then we need to look at bonds formed. And we can see we've got 1 N triple bond N, and that's 1 times 944, which is 944. And I've also now got 8 of these OH bonds, 2 OH bonds per molecule, and I've got 4 molecules, so that's 8 OH bonds. It gives me 8 OHs, which is equal to 8 times 463, which is 3704. And when we add those up together, we get 4648. And again, that's likely to get you another mark in an exam. So I want to work out my delta H. Well, delta H is sum of the mean bond enthalpy of bonds broken minus sum of the mean bond enthalpies of the bonds formed. So here I've got my delta H is equal to 3859 minus 4648, and that gives me an enthalpy change of minus 789 kilojoules per mole. That's quite a straightforward question there. I'm going to move on to another question now, and this time I had to calculate a bond enthalpy, and I'm given the actual enthalpy change for the reaction. In this particular reaction, again, you have to be aware that carbon dioxide is a carbon-oxygen double bond. Obviously, hydrogen is H. Methanol is this, and water is the same as we've looked at in the previous question here. So I follow the same procedure. I'm going to say bonds broken. And what I've got there, you can see I've got 2, I'll highlight them, 2 C double bond O's. So I've got 2 C double bond O's, which is equal to 2 times 743, which is 1486. And I've got 3 HH bonds. As you can see, I've got 3 hydrogens, so 3 HH bonds. And that's what I want to find out. So it's going to be 3. I'm going to call the mean bond enthalpy for the hydrogen-hydrogen bond X. That's my unknown 3X. I then look at my bonds formed. And we can see that I've got 3 CH bonds, 1, 2, and 3. And that's 3 times 412, which is 1236. I've also got a CO bond there. So I've got 1 CO, which is equal to 1 times 360, which is also 360. And then I've got, as you can see, hopefully, I've got 1 OH bond there, and then I've got 2 from my water, so I've got 3 OH bonds. And that's equal to 3 times 463, which is 1389. So I add them up, and that gives me 2985. My bonds broken, just highlight this, my bonds broken is 1486 plus 3x. So again, if I use my equation of that I've looked at here, then my delta H is equal to 1486 plus 3x minus 2985. And it's now simply a case of rearranging that for x. We all obviously know that delta h, it gives you in the question here, is minus 49. So I can actually put in here minus 49. So minus 49 equals 1486 plus 3x minus 2985. So what I'm going to do is just a case of solving this for x. I'm going to add 2985 to both sides, and what we should get then is 2985 minus 49 equals 1486 plus 3x, and then I subtract 1486 from both sides, so I get 2985 minus 49 minus 1486 equals 3x. When you do that sum, you get 1450 is equal to 3x, and therefore x is equal to 483, and that there is your answer. Now, the actual data book value for a hydrogen-hydrogen bond is actually 436. Why then have we got such a big discrepancy? It's very, very important to remember that the actual bond enthalpies will be slightly different from the mean bond enthalpies. So it's important to note that mean bond enthalpies are not the same as the actual bond enthalpies in the reaction. So these values that we're working out, this value here, this mean bond enthalpy here, they'll be slightly different to what the actual true values would be. This is a theoretical way to work out enthalpy changes, or in this case, mean bond, the bond enthalpy. Again, they'll be slightly different to the actual value due to this very important point here. Okay, I'm going to take one last look at an exam question, which is quite a recent exam question based on similar to the last question we've just done. It says then hydrogen fluoride reacts with ethyne as shown in the equation. All compounds are in the gaseous state, and we've been given some mean bond enthalpy data. We've been given the enthalpy change for the reaction here, and we've got to work out the value for the carbon fluorine bond enthalpy in the product. It's exactly the same as how we've done it before. Firstly, we work out the sum of the bond enthalpies of the bonds broken, and we can see here that we've got two CHs and that gives me 2 times 412, that's 824. I've got, as you can see here, we've got one C triple bond C, that's equal to 3837, so I've got one and I've also got two HFs, as we can see there, two HFs, and that's equal to 2 times 562, that's 1124. So then we add these up, and that gives me 2785. And again, that is probably enough to get 1 mark in the exam. We then need to take a look at the bonds formed, the sum of the mean bond enthalpy of the bonds formed. And we can see that we've got 1 2, 3, 4 CH bonds. So I've got 4 CHs, which is 4 times 412, which is equal to 1648. And I've also got this carbon-carbon bond here, which is 348. And what I want to work out then is the bond enthalpy of a CF bond. We can see here that I've got 2 CF bonds. So I'm going to say that we've got 2 CF, which then it can be said is equal to 2x. So when we add these up, we get 1996 plus 2x. So again, using the equation that we've looked at all the way up here, we're going to use this equation again. And we know what my enthalpy change is, it's minus 179. So we would say then minus 179 equals 2785 minus 1996 plus 2x. Okay, so again, we just simply need to rearrange that to get x. So what we get then is 2785 plus 179 equals 1996 plus 2x. And then obviously we subtract 1996 from both sides. 2785 plus 179 minus 1996 equals 2x. So we get 968 equals 2x, and therefore x equals 484 kilojoules per mole. So that is a recent exam question, and one which, when I marked it, quite a lot of people got wrong. But again, if you follow the procedures done here, then you should be fine. I think where a lot of people went wrong when I looked at it is they forgot that CC bond there. So you've got to make sure you include all the bonds that are broken formed and double check that. So you are now well armed to be able to answer any question involving bond enthalpies.